Okay, folks, as we get settled down, I responded to a few posts on Piazza about the project. I hope it helps you to get things clarified in terms of what we are supposed to be doing. The post about the UD chains refinement. And of course, I also saw that some benchmarks are not giving the correlation and all that. So I've been exchanging emails with Nathan to help select a benchmark. But in the meantime, you should be able to reproduce the results with the example in the paper as a starting point, and also write some more complicated branch correlation examples to show the that you are able to deal with them, document them in your report. And so the main idea, of course, here is to be able to understand this framework, implement it, and sort of demonstrate that it does useful stuff on the example in the paper and your own. And we'll, in the meantime, try to post a large-scale benchmark. The problem is that I think the benchmarks which I had suggested to Nathan, they are retired from Spec 95. Paper has been a little older, and there are a couple of generations of benchmark which have emerged ever since. But we'll see if we can pick something and give it to you. There are some suggestions which he's looking at. And if you have any specific other questions, please do come to office hours. We have those right after. And we'll be happy to discuss. Nathan and me will be happy to assist you there. With that, I guess I'm going to get started, and we will now try and finish this loop transformations, which is the last topic we are looking at. And we are going to, from there, move on next week to quick review of register allocation and its used in machine-specific optimization, which will be our last topic. So let's get started. And before we do that, are there any questions about iTest in terms of its understanding, what it does? Any quick questions I'd like to take up, as because we are transiting to another topic, and or if you have those and if you want to discuss one-on-one, you're all, of course, always welcome for the office hours. So I'll pause for a minute, otherwise I'll try and share my screen here. Hopefully all this works well now. I rebooted my machine twice. Can you see it, Jason?
Yes.
Okay, cool. All right. So looks like there aren't any questions. So what we are going to do is move on to this topic of loop restructuring, and we'll see here parallel as well as sequential optimizations that are related to the loop that use the dependence information. So let's look at it, and all these transformations, as against many others that we have seen earlier, like data flow and data dependence, the data flow optimizations like SSA or the traditional data flow, those all work at the medium level IR level, that is quad level, as you know. So it's a part of the middle end. But some of these optimizations, their detection as well as their transformations are done in the end of the front end. So mostly what we call as higher level IR, which is close to the source level. Like at Clang level, you have ASTs which you have loop representation, you have the index variables of the loop, you have the array statements, which are not broken down in terms of the array access patterns and things like that. So a lot of original source information is available, and that is where this analysis is typically carried out. In other words, they're also a part of what we call as source-to-source restructuring or source-to-source compilers, which could be, transforming, one program into another higher level program. That other higher level program, the target could be an optimized one, which could be a sequentially optimized one, or it could be more typically a parallelized one, which has done the parallelization, given it, decomposed it to different cores, and then the second compiler takes over from there, which is a parallelizing compiler. It takes those annotations and then it implements those and generates parallel code at the back end. So that is typically the flow. In short, these are not really done at the middle level or middle end. Having discussed the middle end in depth with all the way SSA and PRE and so on, we have moved up now to the dependence analysis also carried out at the closer to the source level, which is the AST level. In Clang, for example, that will be the level at which the program will be found close to its source. Things will get generated there in terms of dependent systems, etc., and the parallelization will be done. And one typical example could be that you take a sequential C program, do this dependence analysis, and then annotate the parallel loops with the OpenMP pragmas at the source level. What are OpenMP pragmas? Those are the pragmas which could be put on top of loops, such as this is a totally parallel loop and so on, and then given to an OpenMP parallelizing compiler, which will take that loop, which will split it up into multiple cores. It will also do some vectorization, those kinds of stuff. And then it will generate parallel code from there. So that's typically the flow. There are many such compilers out there which actually do this actively in terms of taking a sequential one, converting into an OpenMP annotated code, or some of them even take directly OpenMP code and do some further restructuring based on those pragmas. Also one of the compilers which does this is also called as a ROSE compiler, which was very heavily used for Fortran compilation, which is also a source-to-source restructuring kind of thing. There used to be a compiler called Polaris, developed at UIUC, and its variant, I believe, is now there in Purdue. I forgot the name of that, but it is a source-to-source parallelizing compiler. So I think it starts with C. If I remember it, I'll let you know. So let's start and see what all we can do here. And these, again, as I said, are trying to change one source to the other to get it more efficient. So the first transformation, I'm just going to randomly go through this list of transformations which are there, and all the important ones are sort of covered here. So the first one is called branch unswitching. And what you typically have is what is shown here in this example on the left-hand side. You have doubly nested loop, and then you have a branch which is guarding a statement in the deepest level of the loop about ti being greater than 0. That is multiplying it by a statement and things like that. Otherwise, if it is any other than that condition, which is negative or 0, then we are just initializing a of ij as 0. So this is a typical sort of stencil code many times which does some things to transform a of ij into its change form. So you can see that this is a perfectly nested loop, which is great. And there are a lot of advantages of perfectly nested loops from analysis standpoint and so on. But from performance standpoint, you can easily see here that T of I, which is inside the T of J, for J loop, it's really a problem in the sense it's a branch which is independent of that loop, which is not really dependent on J loop, and it is unnecessarily getting executed there. And so the transformation could be that you move it outside into the I loop. And if you do that, then you can see on the right hand side, we have T of I greater than 0. And then we have the whole loop, which is J loop now goes inside the body of the branch in the then side as well as else side. And the body which is goes into the then side, of course, is the loop statement a of ij equal to a of ij minus 1 times t of I, etc. And of course, the else side of the branch, the statement that goes inside is just a of ij equal to 0. So this is called as the unswitching transformation. So switching transformation, of course, will do the reverse. It will switch this branch inside so that it creates a fully nested loop, and then the loop will get analyzed. So switching transformation is typically only for the purposes of analysis, but unswitching like this is the eventual code that is emitted because of its efficient. So we have, how do we decide on this? So first of all, we have to find out if there is any branch in the deepest level which is independent of the loopness, and we just move that out and then push the loop nest inside for respective ends of the branch. And so this is a fairly easy transformation which relies on that independence. So we could not, of course, move this even outside of I because it depends on Ti depends on I. So if any of the predicates of the branch depends on the surrounding loop, then we cannot move it. That's the stopping condition. But otherwise, we will move it outside. So what are the implications? The conditional test must be independently of the loop out of which we are moving. That's the constraint, and it is always legal if this constraint is met. The frequency of execution is reduced because we are moving it outside. The disadvantage is, of course, as I was mentioning, the loop it's complex now. We don't have any more perfectly nested loop. There's a little bit of code size expansion sometimes, and we might split up the statements which are executing together into different loop nests, and there may not be data reuse. So let's go back and see. So you can see here that, on the right-hand side, we don't have any more perfectly nested loops, so analysis could be jeopardized for the following phases. That's why typically this is done at the end of all the transformations, once all the other are done. And finally, the goal will be to move this out. You can see that the total execution frequency is reduced. However, the loop is not any perfectly nested. And if there was locality between then and else side of the loop, that is now we could have seen there that now this whole J loop executes for all statements there, and of course, since then and else are mutually exclusive, we do not have to worry about the dependencies here. if, of course, the Ti was independent of J. That's under that assumption. We would always see that we'll enter J loop. We will either execute all the then side or we'll execute the else side. So there is no question of dependencies between them. And that's the reason for legality of this. So, however, we have now split up the existence of the statements into two different loop nests, which is for J, and in the I loop we have two nested J loops now. So there may be certain loss of locality because of that reason, in case we decide to do even further splitting based on the restructuring that we are doing. So it really depends. After this, there could be restructuring phase typically. What it implies is this, that there could be a restructuring phase which might cut up these two loops, which are separated now, and might execute it if there are no further dependencies, of course, which is the case here. If there are, then they cannot be. So if, for example, if there is a loop carry dependence here, which is in the I loop nest, there is, of course, nothing we can do. We cannot split this further. But if there isn't, which is the case here, we could, after doing the switching, create these two kind of loop nests and simply execute the I loop in two different ways. One is under greater than condition and second is under else condition. And that could lead to a loss of locality. So it's the further transformation like splitting which might jeopardize that. But for now, for this, just this transformation without splitting, there is no such thing that happens. However, what really is lost here is a perfectly nested loop. But the good thing is the frequencies of the branches are reduced in the sequential sense. So the next one is really a very interesting and important one. This is called as loop peeling, and it's a very simple transformation. It's basically removing the first iteration or the last iteration, and typically this is used as a pre-transformation for doing the loop fusion and the other transformations. So let's look at how this works. So one thing one has to be sure is once we are peeling the first iteration is that the loop executes at least once. And so we had to put a guard here. If n is greater than or equal to 1, then the loop is executes 1. So for example, if n was -1 or 0, obviously the loop will never execute because of the. Make sure it executes at least once by putting this guard at the top. And then what we do is we have the first iteration a of I is equal to x plus y times b of 1. So we will remove that. We will generate even the loop invariant here, which is x plus y, save that into t, and we'll execute the first iteration outside, and then from second to n, we will just use the t there, and we'll just execute the rest of the loop. So because of this reason, you can see that now our trip count of the loop that is peeled, instead of 1 to n, it has gone 2 to n. And you will see later that that's very helpful for us to do the fusion when the trip counts of the loops don't match. Sometimes we do it the first iteration, sometimes we'll do the last iteration, and depending on the alignment that we are trying to seek. So, so the important thing here is this, that we don't know if the trip count is always positive, which is the case for almost all loops. The peel code is to be protected by a zero trip test, which is that it executes at least once. And this is, as I was mentioning, is mainly used for aligning the total number of iterations. If one loop is executing 5 times, another is executing, let's say, 6 times, you can see that we should peel one iteration from that 6-time iterating executing loop, and then we'll fuse the two, which are both now executing 5 times. It also is a good thing because loop invariant, it allows us to do this. And the disadvantage is minor because now you have some more code. In general, loop unrolling, loop peeling, you can see that these are all increasing code size. The next one, which is shown here, is an interesting one, which is called as loop index set splitting. So you can see what is going on here is we have a conditional branch inside the loop, which executes, which is purely dependent on the induction variable of the loop or index variable of the loop, which is going from a particular limit, like greater than 10. And you can see that the loop, the way it will behave is first it will just execute first statement, ai equal to bi plus ci. But then iteration 11 onwards, it will execute both statements. And through that, we can easily see that we can identify this index in between, and we can create two kinds of loops, one which executes till 10 and another which executes from 11 onwards. And that's how it will look. First 10 iterations, just the first statement, 11th onwards, both the statements. And there is no other change that is needed over there. So this is really useful for getting rid of the conditional and implementing it per se as a part of evaluating it and creating the loop nests such as these. Once these happen, you can see that such kind of loop nests coming out of the transformation then are very suitable for fusion, for doing some transformations on them, which we are going to see later. So these are all enabling transformation. Index set splitting is also an enabling transformation, typically like trying to achieve getting rid of the conditional and so on. So as I said again, it's enabling transformation for fusion or getting rid of the conditional, leads to code size expansion. And then there is another use of this transformation which is not clearly noted here, and that's a very interesting use. So let me go to the whiteboard there to show you that use, which is about the index set splitting, what it really allows you to do. This use of transformation is mainly related to parallelization, and it's seen a lot in practice. And it's allows us to really parallelize some loops, which so abstractly here is our loop, which is we are trying to parallelize. And many times, as you know, we just get dependence direction vector. So let's say this is the dependence direction vector that we have seen in the loop. I'm trying to keep it just simple, one-dimensional case. What this means is that we are not able to exactly compute the dependence distance, but we are just able to compute its direction. That if we have a of some f1 here, a reference, and here we have a of f2 here, which is this is the write, this is the read, and if this is our I1 and this is our I2, the consumer IW, let's call it, maybe the write iteration and read iteration, IR. IW, as you know, is for a flow dependence will be IR. That's what we know. But we don't know exact distance. The reason is this, that many times this distance it will be varying. Okay, it will not be fixed. How? So let us take a function here. Let's say this is f1. Here is just of I, and f2 on the other hand is 2I plus 5. So now let us calculate the dependence distance here. Okay, so this is our f2 and that's our f1. So what's the distance, number of iterations that elapse between the producing iteration and the consuming iteration? So distance here is equal to I2 minus I1. And if you do that, this is 2I 2 minus I1 plus 5. So let's say the dependence was occurring when these two were equal. So this is the distance. You can focus on this distance here. So let's say for several pairs this particular dependence is true, such that I1, I2 lie within the bounds. This is within the bounds 1 to n. Now you can see that as you look at the distance as I2 minus I1, when this function is really satisfied, this I2 minus I1, and from this particular equation is going to be equal to I2 plus 5. Okay, so this is all going to be the dependence equation. I'm sorry, I sort of didn't write it carefully here, so let me write it here. The dependence really occurs when I1 is equal to 2I2 plus 5. Okay, now shuffle this particular thing from here. Let's derive this dependence distance by moving something on the right hand side and moving if you look at this, 2I2 minus I1 plus 5 equal to 0, and I2 minus I1 minus I1, let me write it here, sorry, I2 from here let's write it here, I2 minus I1 is equal to minus I2 plus 5. We may have messed this up in terms of true versus anti-dependence, but that doesn't matter. So you can see that as I2 is increasing here, this distance is becoming lesser and lesser and lesser, and at some point it converts from one dependence to the other, and then it starts growing in terms of the dependence distance over here, because it's minus I2 plus 5. And so this distance itself, as I2 grows, will become more and more negative, and it will become an anti-dependence of some sort. Now, remember that if this distance, whatever that is, minus I2 plus 5, either one is dependence preventing, and let's just assume that we have an anti-dependence in this particular case because of the references. Okay, because minus I2 plus 5 is negative, and it is growing, as you can see, with I2. So as the dependence distance grows more and more and more, and it exceeds the loop bounds at certain points, at certain value of I2, the dependence distance will become so large, this particular one, it will, the dependence pair one will stay within the loop iteration space and second will be outside of it. And because of that, the dependence will simply go away. So when the dependence goes away because of increasing dependence distance, in this case, in the negative sense, we will have a case of the dependence simply going away and the loop being parallelizable. So in short, what we have here is a case of a dependence distance which is becoming larger and larger in terms of the absolute value, and because of which the dependence simply going away after a certain number of iterations when the dependence distance exceeds the loop bounds. So we can calculate the index at which this dependence distance exceeds the loop bounds by equating it to it. And then we can say that at this particular point, distance has enormously large value that if one of the references is within, the other is guaranteed to be not within the bounds, and because of which now the parallelization is possible. So we do that calculation based on this dependence equation. And we find out the dependence distance, which is I2 minus I1, which will be in this case minus I2 plus 5. And we will find out the value of I2 at which this distance will exceed the loop bound from where we are, and we'll split that. If that gives us an I2 value at such and such I dash, then we will split the loop from 1 to I dash as sequential, because the dependence is there within that part of the loop. But the second part of the loop from I dash to whatever is upper bound is will execute parallelly. And typically this some of these dependence distances increase very, very rapidly. So just the first few iterations, let's say first 100 iterations or 200 iterations might get sequentially, but from there suddenly the loop becomes parallel, and that is the way the index set splitting works. So it takes the loop, in short, takes this loop, it analyzes it for dependence distance, and the dependence distance, if at what index it becomes, it exceeds the loop bound, upper bound. It finds that out. Let's say that value is I dash. Now what it does is from 1 to I dash, it has a sequential version of the loop and follows it with I dash to U, because there is no dependence now. The dependence distance has exceeded the loop bounds for this particular range. This is a parallel version. And so that way we do the splitting of the range from 1 to U into 1 to I dash. That's sequential. And then I dash to U as the parallel. And that way we can gain a substantial part of the loop getting to execute it in parallel. There are many loops which form in this particular category of generating the I had given an example of anti-dependence, but you can easily work it out using, it doesn't matter whichever dependence it is. just keeps growing, the consuming and producing iterations, the distance between that keeps growing, which could be easily attributable to the first one being just a function of I and the second one being maybe 2 or 3i, something growing much faster. So the distance between these two will be sort of iterations. At each point, suppose if there is a dependence between I is equal to 4 and I is equal to 2 here, as you can see, the distance here was 2. But now if the dependence is between I is equal to 8 and I is equal to 4, you can see that the difference here between these two is 4. So suddenly it has doubled from 2 to 4 and it keeps growing, and at certain point it exceeds the loop bound, so that if the source of the dependence is I1, that plus D becomes greater than U, which is our upper bound. And obviously we can't have I2 outside this space of upper bound, and so the ceases to exist. And from that I1, where it becomes this particular exceeds U, this is our I dash here. This is our where we can, until then we can have sequential loop, and from that wherever this is true up to U, we'll have a parallel loop. So that's very interesting and useful transformation. Any questions before we move? Okay, so let's get back to some other transformations. And this is purely an application of, as you can see, dependence equations, and mainly about the ability to identify where the dependence ceases to exist. This is a useful transformation, which is mainly related to parallelization. And these kinds of patterns, they come across scientific code in many cases. So what is going on here? So we have accumulation, that is AI plus BI is being added here. And some function of that accumulation is being saved in a CI. The programmer, of course, has written a, AI plus BI as T, and then CI is equal to T plus 1 over T, something like that. So if you really analyze the dependencies here, we have a flow dependence, which is from T to T, from first statement to the other. But unfortunately, we also have an anti-dependence, which is from the second statement to the first one, which is a loop one. So the second one is a problematic one, the anti-dependence one. The first one is just fine in terms of loop iteration-based parallelization. But the second one is a problematic one because they both act on the scalar. One writes to the T and second reads from T. And you can easily see here, there's no reason to do it. We should what we call as privatize it, or we should just expand T to T of I. And that is what is done here. We take this variable and we expand it into Tx of I, and we do so by checking that the loop executes at least once and all these other things. And now you can see that each one of the the uses of the T, which is limited to the last use of T, is really limited to the current iteration, and so that is guaranteed here. And that's how we have removed this anti-dependence. And a general form of this is also called as privatization. Why is it called privatization? Is that you can see that the only thing that was going on in the original code is implementing flow dependence via T. the unfortunate consequence of anti-dependence was just because of the namespace of T. So if we allocate each iteration separately to a core and allocate T privately to each of those cores, the effect is exactly the same as what we have this transformation on the right hand side. And so that is the reason why it was also called as privatization of the variables, which introduce this unfortunate anti-dependence. They could be simply given different namespace by allocating them locally, and that takes care of this anti-dependence not being there. And just privatization means everybody having their own copy of T allows us to implement this flow dependence in parallel. So that is a very useful transformation. A broader case of this is privatization, what I just mentioned. So here are some restrictions. The loop must be countable because we have to allocate so many copies, and then the scalars should not have any upward exposed uses. That means the T must be generated within the loop and consumed within the loop, and then the scalar should not be live on exit. Otherwise, we have to make sure that the last value must be copied into the scalar on exit, which is like this over here, T of x n. You can see that that is copied to T, because if T was used outside, which is not most of the time the cases, but in the absence of any analysis, we'll have to do it like this, unless we prove that it's dead. We'll have to generate the last version of T of x into T, and that will be the right value which will be carried outside the loop. And then the other stuff about flow dependencies, which is mostly the case for privatization, they must be loop independent. They cannot be loop carried. The only loop carried dependency is anti-dependence, which is sort of an unneeded dependence. It's eliminated. The problem here could be that the size of the array might be prohibitive. Most of the time, this, as I mentioned, is done as a privatization optimization. The scalar is purely allocated in local memories of each one of the cores that handle the parallelized iterations, and each one has its own copy of T in short. So in that sense, the overhead is not bad at all. That's how it is mostly implemented. So now let's go to the interesting ones. One is loop fusion, which is very, very important. Why is loop fusion important? It's all about data locality. And as you know, when a loop executes, the loop's data is brought into the cache. First time there are misses, but then there are what you call it, the cache is warmed, the different lines are brought in, the further accesses in the loop are found in the cache, and that's why the execution of the loop is good. Now imagine split up loops like the way I have shown here. The first loop is executing for n iterations, and n could be very, very, very large. What will happen is this loop will in BIs and generating AIs and so on. And because it's so big, because it doesn't fit the cache, all the data which is corresponding to early parts of the execution will probably get kicked out, like A1, A2, A3, or B1, B3. They will all get kicked out because the first loop simply needs more space, and there's not enough space in the cache. And so after that, if you execute the second loop separately, Ci is equal to ai divided by 2. Again, whenever we have a references, a1, a2, a3, they will not be found in cache because they're kicked out by the first loop. And because of this, we'll have again cache misses for a of I. And similarly, between second loop and third loop, we'll have misses for c of I. So that's an undesirable element. And so we want to keep these references within the single loopness so that we encounter one and maybe first time we'll take a hit because of the warming issue in the cache. But the second reference, third reference, they will all be found in cache and will be executing very, very fast. So that is why loop fusion. Now, the question is, can we always do it? And if we can do it, then semantic legality wise, what are the reasons when we can do it? What are the reasons when we cannot do it because it's simply not found? So as you can imagine, it's all about maintaining dependencies and not introducing wrong dependencies during the fusion. You can easily see here that if we do the fusion and try to create one big loop, it will have best locality. The question is whether it will be semantically legal or illegal to the left-hand side loopness. So you can see that A of I, which is being generated in the first loop, is being consumed. All of the A of I's are being generated in the first loop nest. On the left side, they're all being consumed in the second loop nest. And that's a forward dependence, which is flow dependence. Now that is preserved by the fused loop. It becomes a dependence which is not carried by the loop anymore, of course, which is intra-iteration dependence. And that is perfectly fine, but A of I and A of I there in statements 2 and 5, they're all fine. It will also promote locality. It will be warmed up right away in the cache, that line, through a write through for A of I, and in number 5 it will be read, so you'll have a very high locality there. Now let us see if that is the case with C of I and C of I plus 1. What kind of dependence is there on the left hand side before we fuse the loop? You can see that all C of I's are generated there, all of them. And then we read them on the right hand side by the last loop. Now you see that is the case here in the fuse loop. You can see that in a given iteration, unfortunately, we have a read going on first, followed by a write. So originally we had a write for C of I, and then we had a C of I plus 1 in the next loop. Once all the writes took place, there were the reads for each one of them, and so the relationship was I'm going to read the new data that is generated in statement 5, whereas this is not the case. Now what is going to happen here is I'm going to read the data here, which is old data from CI plus 1, because that is the first reference that I encounter. And in the next iteration, I overwrite that data in CI. And so that is the stale data I'm reading in statement 8, and then overwriting that, and that violates the loop semantics because it is all about flow dependence, new data being generated in C of I in line 5 and being read in line 8. So that violates the dependence, and that's the problem. So that is what is shown here, whatever I have said so far. So I'll kind of skip that because I think it should be easy to understand. And if not, you can go through this example. But main thing here is the original dependencies where, as I mentioned, S2 which is coming from S2 and S5, they have a dependence because flow dependence. S5 is dependent on S2 because of A of I, and S5 and S8 they also have dependence because of flow. As you can see, S8 is dependent on S5 because it's generating the new data in S5, which is going to get used in S8. So both are floating and forward dependencies, as you could easily imagine. And what are the dependencies in the fuse loop? So we do have the dependence between S2 and S5, flow dependence, which is loop independent now, which is maintained there, which is perfectly fine. So S2, S5 is there. But we do have, unfortunately, dependence here, as you can imagine. S8, S5 depends on S8. And what kind of dependence is that? It's an anti-dependence. So we are going to get into problem, as I mentioned. And so any kind of new introduction of dependencies and the non-obeyal of the original dependencies is trouble, and so we can't do this fusion for the second and third loop. We can certainly do it for first and second. Okay, any questions on this? So what we do is we do the dependence analysis first. We try out a particular transformation and we check using the dependence analyzer whether the dependence analyzer is obeyed in terms of the original dependencies. So, as I said, we can first fuse just the two, and we can leave out the last in terms of fusion, and that will lead us to, of course, gaining on some locality for A, but not gaining in some locality for C. So what are the advantages of loop fusion? One is, of course, increasing data locality and caches. Fusion, of course, makes the loops large and no longer a problem. It used to be a problem in really old machines which had a very small iCache. Larger loop bodies are always good for optimization, scheduling, other, transformations. So how do we really carry out fusion? The first criterion is they must iterate for same number of times. Big problem about fusion is, as I had mentioned earlier, we find loops which may be fusible in terms of the dependencies, but they have different number of iterations. Maybe the first one executes 100 times, second one executes only 95 times. Then what are we going to do? So the second condition was that they must be adjacent because we want to put them together. If there are some other statements in between them, then that could be a problem. And the third one is we should be able to use the same induction variable in the fuse loop. And these conditions are typically the ones which are checked for fusing the loops. So here is an example of that problematic loop in a different way here. So here we have one loop going from 1 to 99 of A of I, and second going from 1 to 98. C of I is equal to A of I plus 1 plus 2. So let's off the bat, if we fuse them just like the previous one, even if their iterations were exactly, number of iterations were exactly equal, let's say. Here they are not, but let's assume a case where they are both 99. And if we fuse them, then that's going to be a problem because originally we have a flow dependence here. In the flow dependence, in the merge version, what we will find is, however, a anti-dependence, because AI plus 1 will be done before AI, just like the previous example. So that will lead to an anti-dependence, and that will violate the semantics, because it will not allow us to use the newly generated values as number 2 for consumption in number 5. Number 5 will use the old values of A and then override those in the next iteration, a new value. So that is if the iteration count, the trip count was exactly equal, just like previous example. In this case, there is one more wrinkle here. We do have trip counts also different for these two adjacent loops. So what we do is, as shown earlier, we do the index set splitting here, or loop peeling. Let's call it loop peeling, and we'll peel the first iteration. So that kind of goes from 2 to 99, the iteration space for the first one. Second one is 1 to 98. You can see now the trip counts of both are 98. And then we can do normalization for the first loop, and then see if the fusion is possible. And here we go. After doing the peeling, we'll take the first loop, we'll normalize it from 0 to 97, and then we will generate the index sets inside accordingly by shifting by 2 and so on, and by shifting by 1 in another case. And then we will analyze if the original semantics is preserved or not. So you can see now that in this right hand side below the mark, we are able to get the correct alignment of respective behaviors A of I and A of I plus 1. How? You can see that, the first index variable that we have shifted there is always shifted by 2, and so it generates a reference there. And the second one is generates a reference from the index variable of the loop, shifting it by only 1, and that allows us to do A of 2 first, so to say, with regard to IB, and then it allows us to shift it by 1, so to say. So the reads occur before the writes, just like in the original semantics, and the trip count is also correct, and that allows us to do the legal fusion of this particular loop. Any questions? All we did here was we peeled the iteration 0 through 99, of course. And then the second thing that we do here was taking the second loop is also converting in that way, and making sure that the after peeling and normalization, we are able to match the alignment of the two loops. In other words, the first loop, if you really carefully see, is sort of made to start after the first iteration. So the first loop is really starting at second iteration. Second loop starts on time, first iteration, and that kind of matches the when the read write takes place for this particular combined loop, and the write takes place before the read. So that is the reason why this fusion is allowed here. Fission, exactly reverse, and it's rather easier to understand. If you really look at this particular left-hand side loop and analyze the dependencies, what is going on here is we find here is dependence between 4 to 3, and that's a flow dependence. Okay. There is another dependence here from 3 to 4, which is flow dependence. And then there is a dependence from B, you can see, all the way to 3 or 2 to 3 because of BI minus 1. And so rather 3 to 2, sorry, it's basically the flow dependence. BI is generated there, in next iteration is consumed. So that's that. And then finally we have a dependence from 4 to 5 because of generation and consumption of C. And so if you laid it out on the right hand side, what is called as a dependence graph, take each one of the things, an arrow from one to the other indicating direction of dependence, distance, etc. You can see that S3 and S4 form a small loop. That S4 depends on S3 and S3 depends on S4 in terms of the data dependence cycle. And because of this, cutting the loop between S3 and S4 is not possible. So that's the reason why you can't cut anywhere randomly in the loop. If it's a cyclic region, you cannot cut across it. You could certainly cut between S1 and S2, sorry, S2 and S3, or you can cut between S4 and S5. So yeah, so these are the things which are shown in the nested fused loops, fission rather, cutting. So again, it is not possible to cut across the cycles, dependent cycles within the loop, but it is a good idea to cut around them because that will not hurt the dependencies. Okay, so same thing is explained here. And rarely is used these days. It's mainly for isolating parallel parts of the loop. That way, if you cut up a loop which was not parallelizable earlier and cut out its non-parallel sequential component, then the remaining component can be given to parallelizer, and it's parallelized, and it can execute nicely without making the whole loop as sequential. So I guess another transformation, and these are fairly easy to understand, so I'm kind of going them rapidly, but please stop me in case you want to have any clarification. Loop reversals. This is another enabling transformation. The main reason for this is to facilitate alignment of loop index spaces for fusion. As you know, the fusion in these two loops, for example, look at these, which are down here, down to 1. The loop is running in reverse mode, and then this one, the one below, is 1 to n. So obviously we cannot fuse these because one is going in the forward direction from 1 to n, the one below. Second one at the top is going from top to n down to 1. So then what we do is we'll try to reverse the direction of the previous one, the one below. Instead of going from 1 to n, we'll try to make it go down from n to 1, and then we'll attempt the fusion. So when is this legal? Of course, that's the big question. This is only legal, as you can imagine, when there is no loop carried dependence. So it's very easy to see here that we don't have any loop carried dependence. But if it were there, and if we reverse the direction of the index variable, an anti-dependence will get changed to a flow, and flow will get changed to an anti, and so that will be illegal. After doing the reversal again, the rules for fusion again apply just like themselves. We must preserve the dependencies. So in this particular case, you can see that we have forward dependence, which is a flow dependence, and that is preserved here in the loopness during fusion. So the rules for fusion apply as they are. Of course, the enabler for that is a reversal, and whether reversal can be done is the question. So I'll just quickly explain this reversal part just to make sure that we understand it. Okay. If we have some simple loop here, a of I is equal to a of I minus 2 plus 1, I going from 1 to n, things like that, you can see that what kind of loop is this? This is a loop which is going forward, for example, increasing. And what kind of dependence is it? We are writing into, let's say, A10. This is the easiest way to do it. When we are in doubt, I is equal to 10. We do a write here. And in I equal to 12, we do a read from this location, A12, A10. We do a read. This is a write. So you can see that if we concentrate on the loop index variables here, the write occurs before the read. So this is the kind of dependence it is, and it is a flow dependence. Now, of course, we reverse the direction of the loop, and this is a loop carried flow dependence. If we reverse the direction of the loop, then what iteration will occur before which one? We'll have I equal to 12 occur before I equal to 10. And so because of that, what will happen is we'll do the read before, and then we'll do the write, and because of which this will become an anti-dependence. Originally it was flow, this will become anti, and this will be legal. So the problem here is, of course, there is a loop carried dependence here, and once we reverse it, the direction of the dependence also reverses from flow to anti and or anti to flow and becomes illegal, and that's why we can't do the reversal on the iteration space here. And of course, the reason we do a reversal is to be able to align the loops for fusion. The rules for fusion don't change, they remain the same. They must preserve and not introduce any additional dependencies. They should make sure that the forward dependencies are preserved and so on. So I hope there are no questions here because we were able to do this reversal for the lower loop because it has no loop carried dependencies. And then once we also could apply to the rules for fusion here. The reason is you can see that the original dependence was flow. And once we do this fusion, we also were able to do the reads only after the writes because of the iteration space. And therefore, we were able to carry out the fusion here. This is the most important final transformation, which we'll focus on as the last transformation. It's called loop interchanging, and it really has a lot of implications. As I was mentioning earlier, the main reason for interchanging is that we are able to use the special locality in a better way. It's a simple example. We have, let's consider it a doubly nested loop, and the outer loop is operating along a row, and the inner one is operating along a column. So what it means is we are operating in a row major manner, which is typically the case. So that's great. So then we have a locality. But imagine the reverse, that the outer loop is going along a column and the inner loop is going along rows, which means we are doing a column major kind of an operation we are staying along a column when we execute the loop. Very rarely any matrix will be laid out in the memory in a column major manner. In fact, Fortran and other languages have conventions because of the libraries that the data layout should be typically row major. So because of which, if the data layout is row major, that is arranged in the memory in a linear manner, row by row, but if we are traversing it by column, then what we do is we bring in a whole bunch of elements at every access. We used only one of them, we hop on to the next row and things like that, rather than staying inside a row and using all the elements which are fetched using the cache attributes, which is basically a line and that is brought in. We don't get to use it. We lose a lot of locality here. And because of that reasons, big performance loss occurs. So you may say, oh, let's go ahead and change the data layout. Obviously, it's a very expensive operation to transform on a matrix, for example, an n-square operation, and it will be expensive. So what we do is we align the loop to the data layout, which is typically along a row major manner. And that basically means many times reversing the loop. Instead of outer loop being column major, we want to make it row major. Bring inner loop out and outer loop in, and that is basically the loop interchanging transformation. So this is one instance where it is used. The second instance is the kind of parallelization that we want to achieve. Typically, the inner loop, if let's say both loops are parallel, the inner loop is exhibiting what we call a special locality in terms of the data references. It is good to vectorize the inner loop. That is, the consecutive references could be something like A of I plus 1, A of I plus 2, A of I plus 3. All the output dependencies that are shown in the inner loop, let's say they are all in the consecutive memory locations. So it will be good to use that as a inner loop, which is vectorized, and the outer loop that is also carrying dependencies. Good to keep this as more coarse-grained parallel form, and therefore loop interchange may be needed to bring in the right kind of loop as inner loop and make the other as the outer loop, if the original code is not in that form. So for both of these reasons, loop interchange and some other cases as well, very important transformation. So here is an example of a loop transformation which is allowed, which goes from J as outer loop to I as J as inner loop. You can see here that in the original left-hand side code, the J loop was the one which was bearing the reference dependence in the less than direction. Now it is the inner loop, which is J is the inner loop, which is bearing the dependence in the less than direction, and that transformation is legal. However, many iteration vectors, if we analyze those, they simply switch the dependence from inner to outer or outer to inner loop, but they enforce it in the correct order still. And they are all about legal transformations in the sense of direction vectors. The only illegal transformation is what I'm pointing out here on this screen, is as shown on the left-hand side. So this corresponds to the direction vector less than greater than, that becomes a trouble. How? So as you can see here, left-hand side example, we have a flow dependence carried by the outer loop here because of the less than enforcement. And of course, the iteration space in the inner loop executes with the vector of greater than, but the origination of the, so this is a flow dependence. The origination of the dependence is done by I direction, I index variable. And after 2 iterations, it is consumed as a flow in the I dimension. Now, if you switch this around, you are going to have a problem, and that problem will be as follows, that the outer loop is now in the greater direction, and because of that particular reason, the dependence will switch from being a flow dependence to an anti-dependence. That is, the consumption of the dependence will not occur in terms of read. The read will occur before write in the J dimension, because the J is the outer loop now. You can try it, this dependence will, instead of being flow, it will become a anti. And so this thing is illegal here. Now you may say that, okay, why don't we do one thing? Let's reverse the direction of this greater than to a less than. Is that possible in this particular loop nest? Because the dependence is anyway carried by the outer loop, which is I loop. Let's reverse it by carrying out reversal. Instead of going from 1 to n, let's go from n down to 1. That is very much possible. If you reverse it, then you can do an interchange. Then it will become less than dependence. You can, in the J dimension, now it will be carried properly because it's less than. So the outer loop will go from 2 to m, inner loop will go from n down to 1, and then we can reverse it and everything will be fine. So what's the catch here? The catch is this: if there are multiple dependencies which are present in the inner loop, then we are hosed here. So assume that if there is a dependence less than in addition to less than greater than, the moment we reverse the direction in the inner loop, the first dependence less than will become less than greater than. And so the same problem will come into being, and we will be again in trouble in terms of not being able to carry the reversal. Because one dependence will simply convert into another one. So, and that will prevent interchange, and therefore the interchange will have to be dealt with using another technique. And that technique here is what is called as loop fusion, the loop skewing. I will just give a brief idea of what it is today, and then we'll continue in the next one. We're almost done with this topic, but this is a very important one, so I don't want to rush it. So what is the brief idea here? The brief idea is this, that less than greater than dependence, somehow if we can convert into less than dependence by manipulating the iteration space, that is the thing to do here. And what we have done here on the right hand side is exactly that. You can see that we have skewed the iteration space of J from 1 to n by boosting it, by multiplying it with a factor f and adding I to it, or multiplying that factor f to I and adding that to J. So now J goes from 2 to 2 plus f times I, and then the upper bound goes from m to m plus f time I. So the whole iteration space get boosted now by multiplying this f times I and adding it to both lower and upper bounds. And of course, we'll recover the original J dash from this because we still have to, of course, read and write at the correct array locations. We are not changing that. It's just that we've shifted the iteration space. We map it back to the original one into J dash, use that for addressing the elements of A. But in that process, as you will see through the analysis next time, the dependence vector has changed now from greater than to a less than. So by choosing the right value of f, we are able to skew the dependence vector as less than, and that is the way we are able to convert this into a less than loop. Even if we have multiple dependencies in the inner loop, such as one less than, you will see that that remains as it is. It doesn't get changed by like a reversal kind of a technique. And we will see the details of how to choose this F and how this gets skewed and so on. It's a very interesting transformation in the next lecture. And that's all for today. And we'll stop here. And again, if you have any questions, please do ask in the office hours of any kind. And of course, we'll also respond on the Piazza and make sure it's addressed. And thanks. And as a fallback option, as I said, use the example and some of your own in the when you test your project 1 and report those. If you're able to find a good benchmark, we'll go ahead and post those as well. And do complete the part 1 and move on to part 2. Thank you. Bye-bye.